So that's one important thing. It's likely that the universe will just expand forever, not recollapse. Another crucial thing is that the future of the universe is a thermal state. Okay? We believe that the universe empties out because of the cosmological constant, so matter and radiation dilute away to nothing. But because of the vacuum energy, the vacuum state is not zero temperature. If you put a thermometer in the universe, 10 to the 100 years from now, it will measure a non-zero temperature of about 10 to the minus 30 Kelvin, as opposed to 3 Kelvin, which we would measure today. So colder than it is now, but not zero. This calculation is the same calculation as Stephen Hawking uses to say that black holes have a temperature and evaporate. So if you believe that, you should believe this. It's just virtual particles in their lowest energy state do not have zero temperature. If that's true, and that lasts forever, so the temperature does not redshift away, the temperature does not dilute away or go down as the universe expands in this case. De Sitter space is the name we give to this empty universe with nothing but vacuum energy in it. It is our future and it has this temperature. If that's true, then there are thermal fluctuations in empty space. We can wait around. You'll usually see these very, very cold photons, but you have infinity to wait. The universe never ends in this scenario. So you get all sorts of fluctuations. Occasionally you will see 2 photons. Occasionally you will see a high energy photon. Occasionally you will see a brain just pop into existence because particles just bumped into each other randomly. It's unlikely, but you have infinitely long to wait. Occasionally you'll see a galaxy or the Earth or an entire universe. If you look at every one region, every one sort of horizon-sized region of this de Sitter space, there's only a finite amount of entropy you can fit into that region, and there's a recurrence time associated with that, which turns out to be 10 to the 10 to the 120 years. Okay? So it's a long time to wait, but finite, so everything that happens repeats itself on that sort of time scale. What this means is that the problem of Boltzmann's scenario, which we said was ridiculous, is a problem of the real world. The lambda CDM scenario, which most cosmologists would bet money is probably right, makes a prediction that we should be Boltzmann brains in an otherwise empty universe. That prediction is false, and yet cosmologists are not really worried about this for reasons which I haven't yet understood. So let me put it yet another way. Here's how we usually draw the universe. In fact, I've already drawn it this way in this talk, starting at something like the Big Bang, and T equals 0, is hot, dense, and smooth. It cools out and empties off over the next 10 to the 10 years, and in the future it sort of fades away, and who knows. But we can predict pretty well what will happen in the future. So a better picture to draw would be this one, going from 0 to 10 to the 100 years. Why did I pick that number? If you think about the stuff we see in the universe, the galaxies, the dark matter, etc., we have a galaxy with 100 billion stars in it. There's a black hole at the center of our galaxy, about 4 million times the mass of the sun. So 4 million solar masses is a lot, but it's nothing compared to the galaxy, right? It's 100 billion solar masses in the galaxy. But if you wait long enough, all that stuff in the galaxy is going to fall into that black hole. It will sort of slowly, gently spiral in, give off gravitational waves, enter the black hole. Stars will die out, etc. That black hole, so then the universe some trillions of years from now will be nothing but black holes. The black holes evaporate, as Hawking taught us. So you can calculate how long it will take those black holes to evaporate. The answer is about 10 to the 100 years. So 10 to the 100 years is the time after which the universe is empty. There's no more stars, there's no more atoms, there's nothing but a few photons moving further and farther away from each other, and then empty space forever. So notice, 10 to the 100 years is longer than 10 to the 10 years, by a lot. This is not to scale. If it were, it's not only true that the first 10 to the 10 years would be the size of 1 pixel. Well, if this was the actual size of 10 to the 100 years, the first 10 to the 10 years is smaller than the Planck length. You can't draw, okay? And yet, this is a wildly parochial view of the universe. A much better view would be this one, because after the black holes evaporate, we're not done. The universe lasts forever, but there is a recurrence time of 10 to the 10 to the 120 years. So this is a more accurate history of the universe, and again, the black hole era of 10 to the 100 years would be less than the Planck length in size on this plot. 10 to the 10 to the 120 years is a long time. And the point is, we can live here. There will be thermal fluctuations in this region. You can roughly count how many observers should be born there, compare them to the observers who are born here, and they almost all should be there. That's the challenge for modern cosmology if you take these arguments seriously. And again, I'm not talking about the multiverse or inflation or the string theory landscape. I'm talking about the theory that most cosmologists believe is probably right. Predicts we should live in empty inner space, and we don't. That's a problem. The final thing from modern cosmology, this is not an experimental thing, but sort of a theoretical prejudice. What about the Big Bang? How seriously should we take the Big Bang? You're often told the Big Bang is the beginning of the universe. Saying what happened before the Big Bang is like saying what is north of the North Pole, etc. That's not right. I mean, it might be right, but there's no reason for us to talk that way. We have no justification for saying that. The truth is just that the Big Bang is not the beginning of the universe. It's the end of our understanding. It's the point where general relativity ceases to be correct. We need to do better than classical general relativity. It could very easily be that there is space and time before the Big Bang. The fact that there are black holes with singularities inside which eventually evaporate and get rid of their singularities is good evidence that probably singularities are not the ends of space and time. They're just a phase that we don't yet understand. So in fact, it's become quite popular to work on models where there is no Big Bang singularity at the beginning of the universe. None of them, so far, I am especially fond of, but at least we should take that possibility seriously. So, the punchline of what we've learned from modern cosmology is that it seems likely that the future evolution will be eternal, that it will not end at any time. The universe is not giving us any evidence it will recollapse. And it's at least plausible that it was also eternal to the past. The Big Bang was not actually the beginning. So in that context, the challenge is, why aren't we random fluctuations in empty space? If you do a simple-minded counting, almost all observers, or almost all rooms like this, should be surrounded by thermal equilibrium. And you're clearly not, so there's something to be explained. Given all that, I'm going to try to now, so that was more or less things that I think are, I can't say everyone agrees, but everyone should agree. There's that. Now I'm going to talk about much more speculative things that even I don't agree with. We're just trying to see, how these problems could be solved. So, my own perspective on this, and this is again very much up for grabs, but the most conservative move in my mind would be to stick with reversible unitary information preserving dynamics. In other words, both classical mechanics, as it's usually understood, and quantum mechanics have two important properties. Number one, they're reversible. So by quantum mechanics, I implicitly mean something like the Everett many worlds interpretation. I'm not worrying about wave function collapse. We could worry about that, but I'm not going to worry about it for this talk. But the point is, if you just believe in the Schrödinger equation, number one, the evolution is perfectly reversible. If I know what the universe is at any one moment in time, and I know the Hamiltonian, I can tell you what it is at all other moments of time. If you know what the past is, you can evolve it to the future, and you can evolve it backwards. And as a consequence of that, you get Liouville's theorem. If you have not perfect knowledge of the universe, but you say, well, it's in one of a certain number of states, and you evolve all those states forward in time, they evolve to the same number of states. No two states evolve to one. No one state splits off into two in the future under these rules. So it is impossible in principle to... So the project of explaining the low entropy of the early universe under these rules is not to find the clever Hamiltonian, which will make it true that many, many robust states all evolve to the same low entropy state. That can't happen. That would violate Liouville's theorem, so we need to be a little bit more clever than that. The other consequence is that time lasts forever. This parameter t in the Schrödinger equation doesn't start at some moment. Every moment in quantum mechanics is just as good as every other moment. That's a consequence, again, of unitary evolution. You just can evolve forever, both forwards and backwards in time. So the idea in the back of your head is that even though general relativity says there's a singularity at the beginning of the Big Bang, somehow quantum gravity will say there's a state that can evolve back before the Big Bang. Well, what do we want? We want a theory. So a theory means a space of states in a Hamiltonian. I will mix up quantum mechanical and classical language, but the same framework applies to both, such that if there is this n shouldn't be there, but it means that the entropy of some region of space, some set of degrees of freedom, if the entropy increases between t and t plus delta t, the entropy goes up a little bit, then it's probably going up a lot, okay? If it's going up after t, it was probably lower before t. That's what we want to be the case, and this is the way that we're trying to get around the Boltzmann brain problem. What we're saying is, if there's an omelet, there was probably an egg, okay? And I'm not saying this at a level of carefulness and rigor that philosophers should be happy with, but you get the idea. I'm just a physicist, I can get away with this stuff. You want more than just fluctuations around equilibrium. You want it to be the case that if the entropy is increasing, then there's probably some very, very large story that we're in the middle of. If there's a brain, there's probably a universe that it came out of, not just thermal equilibrium. Now this seems like it might be a challenge to our model building capabilities, but 3 seconds of reflection reveals that it's not as easy to come up with theories if you don't demand anything else of them that fit that criterion. Just imagine